Okay, thank you. Can everyone hear me okay?
Sounds great.
Perfect. Thanks for the introduction and thanks everyone for being here. Yeah, today I'm excited to tell you about my work to explore the origins of giant planet eccentricities. I'll begin by talking about why this is an interesting problem and how it's related to some other interesting problems in exoplanet science. Before I do so, I'll paint a picture of the solar system so that we can place exoplanets in context. So in the solar system, the planets orbit on nearly circular orbits, that is, they have low eccentricities. Furthermore, the orbits are all nearly coplanar, with orbital motion in the same direction as the stellar spin. And the gas giants in the solar system orbit at large distances outward of the inner rocky planets. And together, these features are explainable by the idea that the planets are born out of a spinning protoplanetary disk where there's sufficient material to build giant planets at large distances. But when we started to observe exoplanets, there were many surprises. So here I'm plotting the population of giant exoplanets detected with every detection method in both semi-major axis and eccentricity. And I'm showing our own Jupiter for comparison. First, there's a population of hot Jupiters. These are very close to their host stars, and they're unlike anything we see in the solar system. They tend to be on circular orbits, but many have high eccentricities as well. There's a population of warm Jupiters, again, unlike what we see in the solar system. There's a relative dearth of these, but again, many of these have high eccentricities. And finally, the cold Jupiter population has even higher eccentricities on average, very much unlike the Jupiter that we have in our own solar system. And together, these features of the giant planet population suggest that there's some additional physics that we need to describe these features. Additionally, many planets exhibit spin-orbit misalignments. So that's shown in the diagram on the left. I'm defining the angle psi as the stellar obliquity. This is the angle between the planet orbit angular momentum and the stellar spin axis. Its projection onto the sky plane, which is what an observer measures as lambda. And on the right, I'm plotting the distribution of lambda for the hot Jupiter population. Many hot Jupiters have high stellar obliquities, and some even exhibit retrograde motion, meaning they're orbiting in the opposite direction of their host star spin. This is again unlike what we see in the solar system and requires some additional physics to explain. So there have been a number of proposed mechanisms for how you can form a hot Jupiter. And so I'll briefly walk through these. So you could first potentially form a hot Jupiter by just forming it where it is, near the star. You somehow have to enhance the amount of material near the star to be able to build a giant planet. Hot Jupiters might migrate inwards through a gaseous protoplanetary disk. Or hot Jupiters could migrate via high eccentricity migration. So Nick alluded to this at the end. Basically, what can happen is if you have a Jupiter born as a cold Jupiter at a large distance, its eccentricity can be excited dynamically. And then it undergoes close pericenter passages in which tidal interactions drag the planet down onto a close-in hot orbit. Now, each of these mechanisms may be responsible for shaping the hot Jupiter population somewhat, but the extent to which each contributes is unclear, and it's unclear if any of these is a dominant formation channel. High eccentricity migration is particularly compelling because it naturally explains why cold Jupiters have high eccentricities. Many of them are sort of just proto-hot Jupiters. But even within this framework, there are many mechanisms that have been proposed for generating eccentricities. So one is planet-planet scattering. So in a multi-planet system, the planets can gravitationally scatter each other onto eccentric orbits. Another mechanism is secular or long timescale chaos in a multi-planet system. And finally, you could have secular perturbations from a distant planet or star, a third body in the system. This is known as the eccentric Kozai-Lidov or EKL mechanism. And this is the mechanism that I'll be focusing on. This mechanism is particularly compelling because many hot Jupiters are observed to have distant planetary or stellar companions. And furthermore, this mechanism can easily generate misalignments between the planet orbit and the stellar spin, which I mentioned are common in the hot Jupiter population. And so this is the mechanism that I'm trying to understand in more detail. And so that brings me to the first of two projects that I'll be describing. So this first project seeks to derive new analytical models to describe the eccentricity evolution of planets subject to this EKL mechanism. So let's take a deep dive into how EKL works. So EKL works in a hierarchical three-body system. So you may have heard of the three-body problem, which attempts to solve for the motion of three bodies interacting gravitationally. So here we look at hierarchical systems, which have a relatively tight inner orbit. So here the star and the giant planet, orbited by a faraway companion on the outer orbit. And this companion can be either another planet or star. In these systems, you can apply the secular approximation, meaning you average over the orbital periods. You care about timescales much longer than the orbital periods. And so to do this averaging, you can treat the orbits as two massive wires. These wires torque each other, exchanging angular momentum, which can lead the eccentricity of the orbits to oscillate and the inclination of the orbits to oscillate as well. And the inclination is shown as this green angle between the orbit normals on the screen. Here I'll show a simulation of how EKL drives the eccentricity evolution. Before I run the simulation, I'll describe what you'll see in each of these three panels. So on the left panel is the orbit of the planet at about 1 AU around its host star, and the third body in this case is way off the screen. It's at 20 AU. The middle panel is a zoom in on the region of about 0.1 AU around the host star, and the dashed line is showing the Roche limit of the system. So you can think of this sort of as where tidal interactions become very strong. Depending on the details of the physics, a hot Jupiter might be disrupted here tidally, or the tidal interactions may capture it and drag it down onto a close-in orbit. So you should just sort of think of this as a close encounter distance where tides are strong. And on the right is a plot of 1 minus the eccentricity of the orbit. 1 minus the eccentricity is proportional to the pericenter distance of the object. So it's tracking how close is the planet getting to the star. And so I'll run the simulation. So you can see that EKL causes the system's eccentricity to oscillate. With each oscillation, I'm marking the point of closest approach with a black dot. And you can see that these black dots march inward over time. The pericenter gets closer with each successive eccentricity oscillation, until finally the planet gets very, very close to the host star, where tidal forces may become important. Now, I'm interested in these black dots. If you can connect the black dots, you can understand the overall eccentricity evolution of the planet from a large distance down to a close encounter distance. And this inward descent is driven by what we call the octupole. It's the octable terms in the Hamiltonian of the system. And so I'm interested in an analytical model for the form and time scale of the octupole level eccentricity evolution to trace the planet's evolution, its pericenter evolution, down to a close encounter distance. And so here are two analytical models that we have developed. So I'll start with the one on the left. So this is a plot of 1 minus the eccentricity of the planet's orbit over time. In blue is the numerical evolution. These are the oscillations that I showed in the simulation. And in orange is our analytical approximation. So here we take a stepwise approach where we try to model the eccentricity evolution during each half cycle. So that's why there are multiple dots per oscillation. So we're modeling the change during each half cycle, and then we piece them all together. And you can see we model the overall eccentricity evolution quite well. This is done in the test particle limit, so taking the mass of the planet to be very small. This is a good approximation in these systems where the mass of the planet is much less than the mass of the star. On the right, so this is a different system now. This is why the time axis is just a little different. We're doing another analytical model. So here we're modeling the envelope of the oscillations with one fell swoop, with a single formula to describe the envelope of the oscillations. And we do this for both the test particle and the general case. So now considering the effect of the planet's mass, you can see that these agree quite well with the numerical evolution. And these models agree quite well over a large range of parameter space. The spread in these regions corresponds to essentially just varying evolutions of the outer orbit of the distant companion in the system. Okay, and so these novel analytical models are applicable beyond just the planetary case. These can apply to any system in which you have this hierarchical triple configuration, down from subplanetary to galactic scales. And you can use these models to estimate the overall eccentricity evolution without having to run a costly numerical simulation. And it's especially useful if you want to run this for a population of systems. So this brings me to my second project. So with this knowledge of EKL in mind, we want to study the population level effect of this mechanism. And we'll be taking a look at the eccentricities of cold Jupiters shaped by the EKL mechanism in stellar binaries. So the systems look like what is shown on the screen, where you have a cold Jupiter around a star, and then orbited by a distant bound stellar companion. And the reason we're interested in cold Jupiters is that the dominant mechanism for hot Jupiter formation should leave its signature on the eccentricities of cold Jupiters. If cold Jupiters are just proto-hot Jupiters, then whatever mechanism is driving hot Jupiter formation should be reflected in the eccentricities of the cold Jupiters. And so this was studied before in this plot shown on the screen. So in black is their simulated eccentricity distribution. And in blue is the observed sample. Red is just an analytical fit to their simulations. Blue is their observed sample. And you see that there's a mismatch between the predictions of EKL from the simulations and the observations. EKL leaves too many planets on circular orbits and not enough at slightly more eccentric orbits to produce a match. And so a broad consensus is that EKL only plays a minor role in sculpting the eccentricity distribution and thus informing hot Jupiters. So this is the question that we're going to revisit with some new insights. So I'll describe the setup of the study that we do. So we construct a large population of cold giant planets in isotropically oriented stellar binaries with FGK-type stars with a uniform binary eccentricity distribution. And we draw the masses and separations from the best observed distributions that we can find. And then we evolve the systems in a hierarchical three-body code for 10 gigayears with this EKL effect, along with the other relevant effects of general relativity, tides, and stellar evolution. And we compute the time-averaged eccentricity distribution of the cold planets. Now, what we do different than previous studies is we test various initial eccentricity distributions for the planets. So the previous study that I showed started all of the planets on circular orbits. But in reality, planet-planet scattering may act on megayear timescales before EKL dominates on longer timescales of megayears to gigayears. And so it's not that these mechanisms are mutually exclusive, but rather they can act in succession to shape the eccentricity distribution. And so I'll show our results on the next slide. So this first panel I'm showing is just an attempt to reproduce the previous study and show that our method is sound. And so you can see the initial conditions are shown with a dashed black line. So they're all on circular orbits here, as previous studies did. And black is the simulated distribution that we obtain. And in blue are the observations. And the p-value shown here is the KS test p-value. Essentially, it tells you the probability that the simulations and the observations come from the same underlying data set. A very small p-value shows that this is very unlikely. The data are very dissimilar. And this is what previous studies found. As you can see, too many simulated planets stay on circular orbits. You can get some higher eccentricities, but you still have too many on circular orbits. But when we start with some initial eccentricity, such as that generated by planet-planet scattering, we can obtain a much better match. So here we start with a Rayleigh distribution of eccentricities. Now, a Rayleigh distribution is the expected outcome of planet-planet scattering. The mean of the Rayleigh distribution depends on the initial conditions of the scattering simulation, but in general, it tends to produce a Rayleigh distribution. And so we test some various Rayleigh distributions with different means. And for slightly higher means, we obtain even better matches, p-values of about 0.5. And all of the simulations agree with the observations within each bin to about 1 or 2 sigma. And in our paper, we test a number of other distributions to obtain more or less good matches. Our general conclusion is that the simulated and observed eccentricity distributions at the present day are consistent for initial distributions from scattering, for instance, with means of about 0.1 to 0.2. So you need some initial eccentricity to do this. Now, what I want to highlight is that we're not just changing the initial conditions. The parameter space of EKL is actually sensitive to small initial eccentricities, and that's illustrated on this plot. So on the x-axis is the initial eccentricity of the planet. On the y-axis is the initial inclination between the planet's orbit and the star's orbit. Theta is the cosine of the inclination. And then the color code here corresponds to the maximum eccentricity reached during a simulation. And you can immediately see that there's some structure in this plot. EKL responds sensitively to the initial eccentricity. If that's a little confusing, let's focus on just this rectangle. So this is a row of constant inclination. And so the leftmost point corresponds to a circular orbit. And you can see that the planet might reach through EKL an eccentricity of about 0.8. But if you start with an eccentricity just a little higher of about 0.1 or 0.15, you can reach an eccentricity of greater than 0.99. And in this case, the planet passes much closer to the star, and you can have much more dramatic effects. So again, EKL is sensitive to just a small amount of initial eccentricity, such as those that can be generated by planet-planet scattering. Here I'm going to compare our work with some previous studies to model the giant planet eccentricity distribution. I'm showing the cumulative distribution function. And so here's the cumulative distribution function of the observed sample. So there's this peak at low eccentricities and a tail out to high eccentricities. Here's the result from the previous study that looked at EKL with initially circular orbits. Remember, too many planets stay on circular orbits. Here are some results from scattering. Again, the outcomes of scattering depend highly on the initial conditions, but in general, scattering produces a Rayleigh distribution, and the present day eccentricity distribution, the solid blue line, doesn't look like a Rayleigh distribution. It has a peak at low eccentricities and a tail out to high eccentricities. But when you combine planet-planet scattering followed by EKL on longer timescales, which is what we do in our work, you can produce a much better match to both the peak and the tail of the distribution. And these results suggest that EKL from stellar companions may be more dominant at driving cold Jupiter eccentricities and thus forming hot Jupiters than was previously thought. As some further evidence for this, I'll discuss what happens when you slice and dice the data based on stellar and planetary multiplicity. So here are our best fit simulations. And here is the distribution of eccentricities for planetary systems that look a lot like our simulations, where you have essentially a three-body system with two stars and a single planet. And you can see that this produces a close match to the simulations. But not every planet is in a stellar binary. Some planets orbit just a single star and they don't have a companion. And in those systems, we should expect to see lower eccentricities on average because they don't have a companion star to be exciting EKL oscillations. And indeed, we see that trend. The single star, single planet sample has more systems at lower eccentricity and fewer systems at higher eccentricity. Although there is some evidence for the action of EKL at higher eccentricities. And so this could suggest that some of these systems may have an undetected stellar or even planetary companion. These data were taken from sort of a heterogeneous sample, and so future observations could systematically search for planetary and stellar companions to confirm or reject this hypothesis. Now, some planets are found in systems in which there's another planet. And so we look at systems that have multiple giant planets. The presence of an additional giant planet can quench the oscillations induced by the distant star. And so in a system with multiple giant planets, we'd expect to see even lower eccentricities on average. And indeed, we do. And so this suggests that in these multiple giant planet systems, perhaps this quenching phenomenon is at play. Of course, in a system with multiple planets, the presence of a second planet could itself induce EKL on the other planet, although the exact nature of this interplay between these effects is a bit outside of the scope of this work. But altogether, these results, looking at the data with different planetary and stellar multiplicities, sort of align with what we'd expect if stellar EKL is driving the eccentricities in these systems. Finally, I'll show some predictions for the mutual inclinations and the stellar obliquities of cold Jupiters. So on the left is the distribution of mutual inclinations. So we start with an initially isotropic distribution. That's the gray shaded curve here. And then over time, the systems tend towards the orange simulated distribution. Systems near 90 degrees tend to get removed from the cold Jupiter distribution. This is because at these higher inclinations, there's more extreme EKL behavior. And so these systems tend to either become hot Jupiters or get tidally disrupted. They get removed from the cold Jupiter population. And so one could test this mutual inclination distribution by measuring perhaps M sin I measurements and comparing these between the single star and multi-star population. And these mutual inclinations could also be testable with Gaia as well. On the right, I'm showing the distributions of stellar obliquities. So this is the spin-orbit angle between the orbit of the planet and the stellar spin. And I'm showing both the in the system obliquity and the sky projected obliquity, lambda, as I defined earlier. You can see many of these systems have high misalignments. So cold Jupiter's obliquities have not really been measured yet, but more distant warm Jupiters have had measured obliquities, and some of these do have high misalignments, which suggests that EKL could be at play in these systems. And this has been particularly found for systems with stellar companions.
Hey, Grant, oh, we're right at the
Okay, cool.
conclusions,
Yeah. So,
please.
so yeah, here are my conclusions. So the existence of hot Jupiters and the eccentricities of cold Jupiters may be together explained by this process of high eccentricity migration. The EKL mechanism is one way to generate these eccentricities. We've obtained new analytical approximations for the octopole level EKL effect, tracing the overall inward descent of a planet with a distant companion. And we find that EKL in stellar binaries can produce a cold Jupiter eccentricity distribution consistent with observations, which suggests that this mechanism may be at play in forming hot Jupiters. And so here are the QR codes that can take you to both of the papers that I discussed. Thank you for your attention. I'd be happy to take any questions.
All right, awesome, Grant. Thanks so much. Again, if you want to put any questions either in the chat or use the raise hand tool, which is under the React button, I believe. Any questions? Yeah, Vanessa, go ahead.
Yeah, really, really nice talk, Grant. I was wondering if your models have anything to say about the evolution with time, and if we have enough data about the time evolution of the eccentricity of these systems, especially in the presence of young systems, to help distinguish these different models.
Yeah, that's a great question. So indeed, we do. We can sort of trace how long it takes, uh, for example, a hot Jupiter or a cold Jupiter to end up, say, becoming a hot Jupiter. Um, and indeed, you could compare these with the ages of systems. It's not something that I've done. It's something I've been thinking about lately, and would be interested in doing more. But certainly, it can come out of the models. Mm-hmm.
Thanks.
Thanks, Vanessa. David.
Hey, Grant, that was a really nice talk. Could you talk a little bit more about not the planet distributions, but rather the star distributions and the binary distributions and what's actually really needed in order to drive this mechanism? Because what are the most appropriate mass ratios that are needed for this, or what are the most appropriate separations that are needed to help drive this? Because it's actually something that we don't understand very well about stellar binaries.
Yeah, this is a fantastic question. So we've tried to draw our distributions, as I mentioned, from the best fit distributions that are observed. So we take the stellar binaries to be from about 50 to 1500 AU. We choose the lower limit of 50 since inward of that, there have been studies that show that maybe these closer binaries can sort of disrupt planet formation. Um, And so that's why we take that limit. We take the eccentricities of the binaries to be a uniform distribution, which we think is sort of close to what the binary eccentricity distribution might be. And so to get stronger EKL effects, you need, generally speaking, you need the binary separation to be closer and more eccentric. So those are the two effects that give you these stronger EKL excitations. Although, like I said, we draw from a large distribution, so not every system in our population is undergoing very strong EKL. So some of them are sort of just quiescently sitting there. I hope that answers your question.
I mean, there's like clearly a longer, detailed, more conversation here that
Sure,
we could have
sure.
at a different time. Okay, thanks.
Yeah, I'd be happy to. Thank you.
Yeah, you guys should chat. All right, thanks so much, Grant. And with that, this closes the first set of presentations for the 2025 ExoExplorers. Thanks so much for your attention.